Human perception often falters when confronted with the absolute extremes of the cosmos. Across the vast expanding canvas of space and time, certain structures stretch our understanding of physics to its ultimate limits, bending light, warping space, and challenging every model of stellar evolution we have ever created. Today we will explore how big TON 618 really is. At the edge of observable reality sits TON 618, a hyperluminous, radio-loud quasar powered by an ultramassive black hole of astonishing proportions. Located roughly 10.4 billion light-years from Earth in the direction of the constellation Canes Venatici, this cosmic structure represents one of the most terrifyingly large singular entities ever identified by modern astrophysics. When we look at TON 618, we are not simply looking at a massive celestial body. We are staring into an ancient gravitational anchor whose sheer scale defies everyday human intuition. To comprehend TON 618, one must first dismantle standard astronomical benchmarks. This object is not a star, nor is it a typical galaxy. It is a superheated engine of radiation surrounding a gravitational singularity so massive that its event horizon could easily swallow entire star systems whole. The energy released by the matter swirling around its center outshines hundreds of trillions of stars combined, making it a beacon across billions of years of cosmic history. Yet, its true identity lies hidden beneath layers of blinding light, where gravity dominates every physical law we know. Unraveling the reality of this celestial giant forces scientists to question how such massive structures could have formed so early in the history of the universe. Over the course of this exploration, we will examine the precise measurements, physical boundaries, and scientific theories that surround this titan of space. If you enjoy this deep dive into the cosmos, please consider liking the video and subscribing to the channel. Feel free to leave a comment below, sharing where in the world you are watching from and what time it is right now. The journey to discovering the true nature of TON 618 is a testament to the evolving capabilities of modern astronomical instrumentation and the persistent refinement of observational techniques. For decades, this incomprehensible structure sat quietly on glass photographic plates, utterly misidentified and overlooked. Its discovery did not occur with a dramatic revelation or an immediate understanding of its vastness. Instead, it began as an unassuming entry in an astronomical survey aimed at mapping faint celestial objects located far from the plane of our own home galaxy. In 1957, astronomers working at the Tonantzintla Observatory in Mexico were conducting an extensive systematic survey of faint blue stars situated away from the galactic plane of the Milky Way. This initiative, known historically as the Tonantzintla Survey, utilized specialized optical telescopes equipped with wide-field Schmidt cameras to capture vast swathes of the night sky. The primary objective of the survey was to identify faint, high-latitude blue objects which scientists at the time assumed were local phenomena. The prevailing belief was that these dim blue dots were white dwarf stars, subdwarf stars, or other old, low-mass stellar remnants residing in the outer halo of the Milky Way galaxy. Among the thousands of faint photographic targets catalogued during this monumental undertaking was a faint, seemingly ordinary point of light, designated as number 618 in the Tonantzintla publication. Thus, the designation TON 618 was born. To the astronomers reviewing the photographic plates in the late 1950s, TON 618 appeared as nothing more than a 16th magnitude faint blue point of light. It possessed no apparent spatial extension, no visible surrounding nebula, and no obvious characteristics that would set it apart from the surrounding stars within our own local galactic neighborhood. It was recorded, categorized, and filed away as an unremarkable candidate for a local faint blue star. For nearly 2 decades, the true identity of TON 618 remained completely hidden behind this mundane label. The scientific context of the 1950s lacked the theoretical frameworks and observational tools necessary to recognize what TON 618 actually was. At that time, the concept of supermassive black holes was largely theoretical, confined to esoteric solutions of general relativity equations. The term quasar had not yet been coined, and the entire discipline of high-energy extragalactic astrophysics was still in its infancy. astronomers had no reason to suspect that a faint point of light captured on an optical plate in Mexico was actually an engine of unfathomable power located at a cosmological distance. The path toward uncovering the reality of TON 618 began to shift during the 1960s, with the emergence and rapid maturation of radio astronomy. Radio telescopes, capable of detecting non-thermal radio waves emitted from cosmic sources, began surveying the skies and discovering strange points of radio emission that corresponded directly to faint optical dots. In 1963, Dutch astronomer Martin Schmidt made a major breakthrough while studying one such object, known as 3C273. By analyzing its optical light spectrum, Schmidt realized that the puzzling emission lines in its spectrum were actually standard hydrogen lines shifted dramatically toward longer, redder wavelengths. This phenomenon, known as cosmological redshift, demonstrated that these point-like sources were moving away from Earth at tremendous fractions of the speed of light due to the expansion of space itself. According to Hubble's law, a high redshift meant that an object was situated billions of light-years away. To be visible at such extreme distances, these objects had to be emitting energy at levels thousands of times greater than an entire galaxy of hundreds of billions of stars. Yet all this energy was emanating from a region no larger than a solar system. These mysterious entities were labeled quasi-stellar radio sources, a term that was eventually shortened to quasars. The discovery of quasars sent shockwaves through the scientific community and triggered a massive re-evaluation of existing star catalogues. Astronomers realized that many objects previously catalogued as local faint blue stars were actually distant quasars residing at the edge of the observable universe. Systematic spectral follow-up programs were initiated globally to analyze the light of blue point sources identified in earlier photographic surveys. In the 1970s, astronomers turned their attention to radio surveys and optical spectroscopy of high-latitude blue objects, including candidates from the Tonnant-Zintler survey. Radio surveys, such as the B2 catalogue, compiled using the Northern Cross radio telescope, began identifying strong radio emissions associated with specific optical coordinates. When astronomers aligned optical photographic plates with high-precision radio positions, TON 618 stood out as a strong candidate for a radio-loud quasi-stellar object. The definitive revelation occurred when astronomers obtained high-resolution optical spectra of TON 618. Spectroscopy involves splitting light into its component colors to analyze emission and absorption lines, which serve as chemical and physical fingerprints of the emitting source. When scientists analyzed the light coming from TON 618, they did not find the typical absorption spectra of a white dwarf star residing in the Milky Way halo. Instead, they observed extremely broad emission lines of ionized hydrogen, carbon, and silicon shifted dramatically toward the red end of the electromagnetic spectrum. The measured redshift of TON 618 was determined to be 2.219. In the realm of observational cosmology, a redshift value of 2.219 carries staggering implications. It indicates that the light we are receiving from TON 618 today has been traveling through expanding space for approximately 10.4 billion years before reaching our instruments on Earth. Because light travels at a finite speed, observing an object 10.4 billion light-years away means we are viewing it as it existed 10.4 billion years ago, when the universe was only about 3.4 billion years old, roughly 25% of its current age. The calculation of this immense distance instantly transformed the scientific understanding of TON 618. What had once been categorized as a dim, low-mass star in our cosmic backyard was suddenly revealed to be an absolute colossus of the early universe. To be visible at a distance of 10.4 billion light-years, TON 618 had to be emitting an extraordinary amount of radiation across the entire electromagnetic spectrum, from radio frequencies to ultraviolet and optical wavelengths. Calculating the absolute bolometric luminosity of TON 618, the total energy output across all wavelengths, revealed a value that strained credulity. TON 618 was emitting radiation at a rate roughly equivalent to 140 trillion times the total luminosity of our Sun. Put another way, TUN 618 was shining brightly enough to outshine all the stars in the Milky Way galaxy combined by a factor of more than 400. It was not just a quasar, it was one of the most luminous quasars ever detected in the entire history of astronomy. This immense luminosity immediately raised fundamental questions regarding the energy source powering TUN 618. Nuclear fusion, the process that powers ordinary stars like our Sun, is inherently inefficient, converting less than 1% of mass into energy. Nuclear fusion could not physically account for the sustained emission of 140 trillion solar luminosities within a compact region, without requiring an impossibly vast amount of mass packed into an unstable spatial volume. The only physical mechanism known to modern physics capable of generating such extreme energy output with high efficiency is gravitational energy conversion via accretion onto a supermassive black hole. As matter falls toward a dense central mass, gravitational potential energy is converted into kinetic energy and thermal energy through friction, shock waves, and magnetic interactions within a rotating accretion disk. The extreme thermal conditions within the inner regions of this accretion disk cause matter to heat up to millions of degrees, releasing tremendous amounts of radiation before crossing the event horizon. However, the sheer luminosity of TUN 618 introduced an even more profound puzzle regarding its underlying central engine. Physics dictates that there is a strict theoretical maximum brightness that a celestial body powering itself through accretion can reach before its own radiation pressure pushes away incoming matter, halting further growth. This limit is known as the Eddington limit. For a black hole to shine with a luminosity of 140 trillion suns without blowing away its fuel supply through radiation pressure, the central gravitational pull must be overwhelmingly powerful. By applying standard physical laws connecting luminosity, radiation pressure, and gravitational force, astrophysicists realized that the central black hole driving TUN 618 could not be an ordinary supermassive black hole like those found at the centers of local galaxies. Sagittarius A star, the supermassive black hole at the center of the Milky Way, possesses a mass of roughly 4 million times that of our Sun. The supermassive black hole in the galaxy Messier 87, famously imaged by the Event Horizon Telescope, weighs approximately 6.5 billion solar masses. The preliminary estimates derived from the luminosity and spectral features of TUN 618 pointed toward a mass scale that dwarfed both of these well-known objects by orders of magnitude. The spectral lines observed in TUN 618 showed extreme Doppler broadening, indicating that gas in the broadline regions surrounding the central engine was moving at velocity scales reaching several thousand kilometers per second. Applying Keplerian laws of motion to these gas velocities provided direct mathematical evidence that the central gravitational anchor possessed a mass measured in tens of billions of solar masses. Thus, over the span of several decades, TUN 618 underwent a dramatic conceptual evolution within the annals of astrophysics. It transitioned from an obscure, misidentified dot on a photographic plate captured in Mexico into a fundamental benchmark for cosmic extremes. It pushed the boundaries of what scientists believed was possible regarding the growth and scale of black holes in the early universe. What began as item number 618 in a catalogue of faint blue stars ultimately proved to be an ancient hyperluminous quasar containing one of the most massive black holes ever recorded by human civilization. To comprehend the staggering visual power of TUN 618, one must look beyond the dark gravitational singularity at its heart and examine the brilliant chaotic structure surrounding it. A quasar is fundamentally an astrophysical engine, driven by the most efficient energy conversion mechanism permitted by the laws of physics, gravitational accretion onto a central black hole. While a black hole itself emits no light, the environment immediately outside its event horizon becomes an arena of violent particle interactions, magnetic field amplification, and hyperthermal radiation. In the case of TUN 618, this surrounding environment generates a total energy output equivalent to 140 trillion suns, making it one of the most luminous powerhouses in the observable universe. At the core of this cosmic engine lies the accretion disk, a vast flattened structure composed of superheated gas, dust, and ionized plasma orbiting the central mass. As matter from the surrounding host galaxy is drawn inward by the gravitational pull of 66 billion solar masses, it cannot fall directly toward the event horizon due to the conservation of angular momentum. Instead, the infalling gas begins to swirl, forming a massive rotating structure. Matter, located closer to the central singularity, orbits at significantly higher speeds than matter positioned further out, establishing a steep differential rotation profile across the disk. This differential rotation generates intense fluid shear within the accreting gas. Adjacent layers of plasma rub against each other at extreme orbital velocities, creating friction on a scale that defies terrestrial imagination. However, simple molecular viscosity alone is entirely insufficient to drive the observed accretion rates of hyperluminous quasars, like TON 618. To account for the rapid transport of angular momentum outward, which allows gas to continuously lose energy and spiral inward, astrophysicists rely on magneto-hydrodynamic processes, most notably the magneto-rotational instability. Magnetic fields threading through the conductive plasma of the accretion disk become stretched, twisted, and amplified by the differential rotation. These tangled magnetic fields act like elastic bands embedded within the gas, coupling inner fast-moving layers with outer slower-moving layers. This magnetic tension effectively transfers angular momentum outward, away from the center, allowing huge volumes of matter to shed their orbital energy and fall inward toward the event horizon. As this mechanical energy is extracted from the infalling matter, it is converted directly into thermal energy, heating the disk to temperature scales reaching hundreds of thousands, and in some inner regions, millions of degrees Kelvin. At these hyperthermal temperatures, the gas becomes completely ionized, reducing atoms to a chaotic sea of free electrons and positive atomic nuclei. This state of matter, known as plasma, interacts continuously with the intense local electromagnetic radiation field. The primary source of thermal radiation in the outer and middle regions of the accretion disk is blackbody radiation. Because the surface area of TON 618's accretion disk spans hundreds of astronomical units, the total surface area emitting this thermal radiation is immense. Each square meter of the disk glows with incandescent intensity, emitting photons continuously across the ultraviolet, optical, and infrared spectra. As plasma spirals closer toward the inner edge of the accretion disk, orbital velocities approach significant fractions of the speed of light. In this inner region, relativistic effects described by Albert Einstein's theory of general relativity become dominant. Space itself is severely dragged around the rotating black hole in a phenomenon known as frame dragging. Plasma swirling within this ergosphere experiences extreme gravitational time dilation and intense tidal forces. The kinetic energy possessed by electrons and ions reaching these relativistic speeds is constantly transformed into high-energy photons through thermal collisions and magnetic interactions. To quantify the sheer scale of energy production within TON 618, astrophysicists examine the concept of mass-energy conversion efficiency. In standard nuclear fusion, such as the proton-proton chain operating inside the core of our Sun, hydrogen nuclei fuse to form helium, converting approximately 0.7% of the rest mass into pure energy according to the famous equation where energy equals mass times the speed of light squared. While nuclear fusion is extraordinarily powerful compared to chemical combustion, it is remarkably inefficient when measured against gravitational accretion. For a non-rotating black hole, the theoretical mass-energy efficiency of accretion is approximately 5.7%. However, if the central engine of TON 618 is a rapidly rotating black hole, a Kerr black hole, the inner boundary of the accretion disk, known as the innermost stable circular orbit, moves significantly closer to the event horizon. In a maximum rotation scenario, the mass-energy efficiency of an accretion disk can reach as high as 42%. This means that nearly half of the rest mass of infalling matter is converted directly into radiant energy before ever crossing the point of no return. Generating a luminosity of 140 trillion times that of the Sun requires a continuous supply of fuel consumed at a rate that is difficult to process. To sustain this energy output, Ton 618 must consume matter at a rate of several hundred solar masses every single year. This corresponds to the central black hole swallowing the equivalent of multiple Earth masses every second, or entire stellar systems on a weekly basis. Millions of tons of gas pass through the inner accretion disk continuously, being converted into blinding light before vanishing forever beyond the event horizon. The physical properties of the light emitted by Ton 618 reveal further details regarding its internal dynamics through a process known as continuum and line emission. As light generated in the ultra-dense inner accretion disk streams outward, it passes through surrounding clouds of lower density gas located further away from the central engine. This surrounding region is divided into the broad line region and the narrow line region, categorized by the specific shapes of the spectral lines observed by astronomers on Earth. In the broadline region of Ton 618, high-energy ultraviolet photons from the accretion disk strip electrons away from atoms of hydrogen, helium, carbon, nitrogen, and silicon, creating ionized clouds of gas. Because these clouds are located relatively close to the gravitational well of the 66 billion solar mass black hole, they orbit at velocities of thousands of kilometers per second. When astronomers collect the light from Ton 618, the Doppler effect causes light emitted by gas moving toward Earth to be shifted towards shorter wavelengths, while light from gas moving away is shifted toward longer wavelengths. This velocity dispersion smears the discrete spectral emission lines into broad, wide spectral features. The extreme width of these broad emission lines in Ton 618 serves as a direct chemical probe of the intense gravitational field driving the gas dynamics. However, the generation of light in a hyperluminous quasar is not entirely a one-way path of radiation streaming into space. The overwhelming intensity of the generated light exerts physical forces back onto the infalling gas. Photons streaming outward collide with free electrons in the surrounding plasma through a scattering mechanism known as Thomson scattering. Each photon collision transfers momentum outward, creating radiation pressure that acts directly against the inward pull of gravity. This fundamental competition between inward gravitational attraction and outward radiation pressure leads to an absolute physical boundary known as the Eddington limit. If the luminosity of an accretion disk exceeds the Eddington limit for a given mass, the outward push of radiation pressure overwhelms gravity, blowing the surrounding gas clouds away and starving the black hole of fuel, which subsequently lowers the luminosity back down to stable levels. Therefore, for Ton 618 to maintain a steady luminosity of 140 trillion solar luminosities without blowing away its own accretion disk, its central mass must be proportionally massive. The mathematical balance between gravity and radiation pressure establishes that only an object weighing tens of billions of solar masses could physically hold on to its fuel while shining with such sustained brightness. Beyond the thermal radiation produced directly by the accretion disk, high-energy interactions within quasars frequently produce non-thermal radiation across the X-ray, gamma-ray, and radio bands. Above the inner region of the accretion disk, a cloud of hyperhot relativistic electrons forms a structure known as the corona. Photons emitted by the cooler optical and ultraviolet regions of the disk pass through this high-energy corona and undergo inverse Compton scattering. During this interaction, low-energy photons collide with high-speed electrons, gaining huge amounts of energy and being boosted into hard X-ray and gamma-ray frequencies. Furthermore, Ton 618 is classified as a radio-loud quasar, indicating that a significant portion of its total energy is emitted at radio frequencies. In radio-loud systems, powerful magnetic field lines thread the inner accretion disk and the rotating event horizon, creating a magnetic funnel aligned with the spin axis of the central engine. Relativistic plasma is channeled into these magnetic funnels, accelerated to speeds exceeding 99% of the speed of light, and launched outward perpendicular to the accretion disk as massive relativistic jets. As electrons within these collimated jets spiral around intense magnetic field lines, they emit synchrotron radiation, which dominates the low-frequency radio spectrum. These jets carry vast quantities of mechanical and magnetic energy out into the intergalactic medium, traveling over distances that can exceed the physical dimensions of entire host galaxies. Though the jets themselves originate in a region no larger than our solar system, their energy feedback impacts surrounding intergalactic space for millions of light years. The total energy balance of TON 618 represents an extreme state of matter and energy. The sheer density of radiation within the inner light years of this quasar creates a photon field so intense that it dominates the local thermodynamic equations. Gas falling toward the horizon is bathed in an environment where light acts as a physical fluid, exerting drag and pushing against material streams. Yet, despite this tremendous radiative barrier, the crushing gravitational field of 66 billion solar masses continuously prevails, pulling vast streams of gas into the inner accretion disk and sustaining the engine. In summary, the light of TON 618 is not generated by a quiet, steady burn like that of a star, nor is it the brief explosive flash of a supernova. It is the continuous, hyper-efficient conversion of gravitational potential energy into electromagnetic radiation across the entire spectrum. Through the combined forces of fluid shear, magnetic turbulence, relativistic frame dragging, and high-energy particle collisions, the accretion disk of TON 618 transforms in falling matter into a beacon that has travelled across 10.4 billion years of expanding space, offering modern astrophysics a view into the violent physics of the early universe. Determining the mass of an object situated 10.4 billion light-years away is one of the most astonishing technical feats of modern observational astrophysics. Because TON 618 appears to our ground-based and space-based telescopes merely as an unresolved point of light, scientists cannot simply photograph its central engine or directly resolve the physical boundary of its black hole. Instead, astrophysicists must rely on indirect spectroscopic measuring techniques that utilize the fundamental laws of motion, gravity, and optics. The primary tool responsible for unlocking the true scale of TON 618, leading to its calculated mass estimate of 66 billion solar masses, is a powerful methodology known as reverberation mapping. To understand reverberation mapping, one must first analyze the geometric layout of the region immediately surrounding a supermassive black hole. At the very center lies the event horizon, wrapped in the blindingly bright accretion disk. Surrounding this central continuum source, at a much larger radius, sits the broadline region. The broadline region consists of dense, fast-moving clouds of gas orbiting within the deep gravitational potential well of the black hole. When the central accretion disk fluctuates in brightness, it emits bursts of high-energy ultraviolet radiation that travel outward through space. As this radiation reaches the clouds in the broadline region, it ionizes the gas, causing the atoms within those clouds to glow and emit specific broad spectral emission lines. Because light travels at a finite, measurable speed, approximately 300,000 kilometers per second, there is an inherent light travel time delay between the instant the central accretion disk brightens and the moment the surrounding broadline region gas responds by emitting enhanced spectral lines. This light travel delay forms the foundation of reverberation mapping. By continuously monitoring a quasar over extended periods, often spanning months, years, or even decades, astronomers capture the subtle brightness variations of the central accretion disk. Then, they track how long it takes for those exact same brightness fluctuations to echo or reverberate off the outer broadline region gas clouds. The measured time delay directly yields the physical distance between the central black hole and the inner boundary of the broadline region. The mathematical relationship is remarkably straightforward. The radius of the broadline region equals the speed of light multiplied by the observed time delay. For an ordinary supermassive black hole, this light travel delay might be a matter of weeks or months. However, in the case of a behemoth like TON 618, the broadline region is positioned vast distances away from the central engine due to the sheer intensity of the central luminosity. Photons emitted from the inner accretion disk must travel for many light years through space before reaching the surrounding broadline clouds, resulting in a time delay measured across multi-year observational baselines. Once astrophysicists establish the physical radius of the broadline region, they require a second vital variable to calculate the central mass, the orbital velocity of the gas clouds within that region. Measuring gas velocity does not require tracking individual clouds moving across the sky, which would be impossible at cosmological distances. Instead, scientists measure orbital motion by analyzing the Doppler broadening of spectral lines. When an ionized gas cloud in the broadline region orbits the central mass, part of its trajectory moves rapidly toward Earth, while another part moves rapidly away. According to the Doppler effect, light emitted from material moving toward the observer is compressed into shorter, bluer wavelengths, whereas light from material moving away is stretched into longer, redder wavelengths. When telescopes capture light from millions of gas clouds orbiting in every direction, the individual Doppler shifts blend together, stretching a normally narrow spectral emission line into a wide, flattened feature. In the optical spectrum of TUN 618, astronomers pay particular attention to broad emission lines, such as hydrogen beta and magnesium 2, as well as high ionization lines like carbon-4 in the ultraviolet spectrum. By carefully measuring the full width at half maximum of these emission lines, astrophysicists calculate the velocity dispersion of the orbiting gas. The spectral broadness observed in TUN 618 reveals gas moving at extraordinary orbital speeds, reaching 7,000 kilometers per second or higher. These colossal velocities indicate that the gas is trapped in an exceptionally deep gravitational well, orbiting a central mass of unimaginable density. With both the physical radius of the broadline region and the orbital velocity of the gas in hand, calculating the mass of the central engine becomes an application of classical Newtonian mechanics modified for relativistic systems. Assuming the gas clouds in the broadline region are in virial equilibrium, meaning their motion is dominated primarily by the gravitational pull of the central black hole rather than thermal expansion or radiation pressure, astrophysicists apply the virial theorem. The central mass is calculated as a dimensionless structural scale factor multiplied by the radius of the broadline region, multiplied by the square of the gas velocity, and divided by the universal gravitational constant. Applying this virial equation to the spectroscopic parameters measured for TUN 618 yields the central value that shocked the scientific community, approximately 66 billion times the mass of our Sun. To place this number into perspective, 66 billion solar masses represents roughly 15,000 times the mass of Sagittarius A star at the center of the Milky Way, and 10 times the mass of the black hole in Messier 87. However, a rigorous scientific evaluation of TUN 618 requires addressing the inherent uncertainties, systematic errors, and ongoing debates surrounding mass estimation techniques in high redshift astrophysics. Science does not treat 66 billion solar masses as an absolute, unyielding fact carved in stone. Rather, it is an empirical calculation accompanied by significant statistical margins of error. Measuring masses at a redshift of 2.219 introduces several complex observational challenges that astrophysicists actively work to refine. One primary source of potential error lies in the dimensionless structural scale factor, usually denoted as F. This factor accounts for the unknown three-dimensional geometry, inclination angle, and velocity distribution of the broadline region clouds. Is the broadline region structured as a thin rotating disk viewed face-on, a spherical cloud distribution, or an outflowing conical wind driven by radiation pressure? Depending on the assumed orientation and structural dynamics, the structural scale factor can introduce systematic uncertainties of up to 50% or more into the final mass value. Another critical consideration is the potential influence of radiation pressure on the gas dynamics of the broadline region. The virial theorem assumes that gravity is the sole dominant force dictating the orbital motion of broadline gas. Yet, as established, TUN 618 emits radiation at an astonishing level of 140 trillion solar luminosities. The intense flux of photons streaming outward from the accretion disk exerts a continuous, powerful push against free electrons and ions within the broadline region clouds. If radiation pressure significantly counteracts the inward pull of gravity, gas clouds can orbit at lower velocities than gravity alone would dictate, or, conversely, outward radiation forces could mimic high rotational velocities by accelerating material into powerful outflows. When radiation pressure corrections are incorporated into the mathematical modeling of high luminosity quasars, Some theoretical frameworks suggest that traditional virial estimates might overestimate the mass of the central engine. Conversely, other astrophysical models argue that broad-line region gas clouds are sufficiently dense and self-shielding, meaning that radiation pressure affects only a thin surface layer, while the bulk orbital trajectory remains firmly governed by central gravity. February, direct time-domain reverberation mapping for high redshift quasars like TON 618 requires decades of continuous monitoring due to cosmological time dilation. Because TON 618 possesses a redshift of 2.219, time intervals observed from Earth are expanded by a factor of 1 plus the redshift, or roughly 3.22 times longer than local time in the quasar's rest frame. A physical variability process taking 1 year near the black hole takes over 3 years to observe through terrestrial telescopes. Consequently, astronomers frequently rely on single-epoch broad-line region scaling relations. Single-epoch scaling relations utilize the well-established empirical relationship between the overall continuum luminosity of a quasar and the physical size of its broad-line region. Because brighter quasars consistently possess larger broad-line regions, measuring the optical or ultraviolet luminosity from a single high-quality spectrum allows scientists to estimate the broad-line region radius without waiting decades for time delay measurements. However, extrapolating size-luminosity relations established on lower luminosity, local quasars up to ultraluminous objects like TON 618 introduces potential calibration errors, as the physical properties of gas at extreme luminosities may deviate from linear expectations. Despite these recognized observational uncertainties, independent analysis of the optical, ultraviolet, and radio spectra of TON 618 consistently points toward an extraordinarily massive object. Even if conservative statistical error margins are applied, accounting for potential geometry factors, radiation pressure corrections, and scaling relation uncertainties, the absolute minimum lower bound for the mass of TON 618 remains solidly above 20 to 30 billion solar masses, while upper estimates reach as high as 70 to 80 billion solar masses. The value of 66 billion solar masses represents the median statistical baseline supported by standard empirical broad-line calibrations. The realization that an object of 66 billion solar masses existed when the universe was only 3.4 billion years old remains one of the most compelling challenges in modern cosmology. The techniques used to measure TON 618 do not merely yield a dramatic number for headline statistics, they provide crucial empirical boundary conditions for models of galaxy formation, black hole growth, and high-energy particle physics. By continually refining reverberation mapping algorithms, improving high-resolution optical spectroscopy, and utilizing advanced space observatories, astrophysicists continue to test and validate the cosmic scales of this absolute giant. To comprehend the staggering scale of TON 618, one must move beyond abstract figures of solar mass and examine the fundamental physical boundary defining its presence in space, the event horizon. In the framework of general relativity, a black hole is not a solid sphere composed of matter in a traditional state. It is a region where mass is concentrated to such an extreme density that the curvature of space-time becomes infinite at its core, creating a central gravitational singularity. Surrounding this singularity is an invisible spherical threshold known as the event horizon, the absolute point of no return beyond which the escape velocity exceeds the speed of light in a vacuum. The mathematical formulation describing the physical dimensions of this boundary was derived by German physicist Karl Schwarzschild in 1915, just months after Albert Einstein published his theory of general relativity. Solving Einstein's field equations for a static, non-rotating spherical mass, Schwarzschild demonstrated that every given quantity of mass possesses an inherent critical radius. If an object is compressed within this specific distance, its gravitational pull becomes so severe that spacetime collapses inward faster than light can propagate outward. This distance is defined as the Schwarzschild radius. Calculating the Schwarzschild radius of any celestial object involves a precise mathematical relationship governed by 3 fundamental physical constants: the universal gravitational constant, the speed of light in a vacuum, and the total mass of the system. The Schwarzschild radius is directly proportional to mass, Mathematically, the formula states that the Schwarzschild radius equals 2 times the gravitational constant multiplied by the mass divided by the speed of light squared. Because the gravitational constant and the speed of light are fixed properties of our universe, the equation demonstrates a simple linear proportion. Doubling the mass of a black hole doubles the physical radius of its event horizon. When this classical formula is applied to standard celestial bodies, the resulting critical distances highlight the extreme nature of space-time curvature. For example, to transform Earth into a black hole, its entire mass would have to be compressed into a sphere with a Schwarzschild radius of less than 9 millimeters, roughly the size of a marble. If our Sun were to collapse into a black hole, its Schwarzschild radius would measure approximately 3 kilometers, spanning a total physical diameter of just 6 kilometers. However, when this exact same relativistic equation is applied to the central engine of TON 618, using its estimated mass of 66 billion solar masses, the calculated physical dimensions escalate into scales that surpass traditional astronomical benchmarks. Multiplying the Schwarzschild radius of a single solar mass, roughly 3 kilometers, by 66 billion yields a Schwarzschild radius of approximately 195 billion kilometers for TON 618. Because the event horizon is a three-dimensional sphere surrounding the central singularity, measuring the full width across this boundary requires doubling the radius to determine the total physical diameter. Doubling 195 billion kilometers reveals an absolute event horizon diameter of approximately 390 billion kilometers. In terms of astronomical units, where 1 astronomical unit represents the average distance between Earth and the Sun, roughly 149.6 million kilometers, the event horizon of TON 618 spans an astonishing diameter of approximately 2,600 astronomical units. To grasp the physical reality of a boundary measuring 390 billion kilometers across, one must examine what the event horizon actually represents from a physical and mathematical standpoint. The event horizon is not a physical shell made of material substances. It possesses no tangible surface, no solid crust, and no material resistance. An observer falling through the event horizon would encounter no physical wall at the threshold itself. Instead, the event horizon is a causal boundary in the structure of space and time. Outside the event horizon, space and time maintain their familiar orientations. A moving object or particle can choose to travel in various directional paths through three-dimensional space, and its future light cone allows for potential trajectories that lead away from the gravitational source, provided sufficient propulsive energy is applied. However, as material crosses the threshold of the Schwarzschild radius, the intense curvature of space-time undergoes a fundamental mathematical coordinate inversion. Inside the event horizon, the radial direction toward the central singularity becomes an inevitable temporal direction rather than a spatial path. Moving forward in time becomes mathematically identical to moving inward toward the singularity. Just as no physical object can travel backward into yesterday, no particle within the 390 billion kilometer diameter of TON 618 can travel outward toward the event horizon. Furthermore, the light travel time required merely to cross the event horizon of TON 618 provides a vivid demonstration of its physical volume. Light, traveling at its ultimate cosmic speed limit of approximately 300,000 kilometers per second, covers roughly 1 billion kilometers every hour. To travel across the full 390 billion kilometer diameter of TON 618's event horizon, a beam of light would require approximately 390,000 seconds, which equates to more than 108 hours or roughly 4.5 days of continuous travel. If a photon were directed straight through the center of TON 618, entering the event horizon on one side and hypothetically continuing in a straight line, it would spend more than 4 days traveling through the interior domain of the singularity before reaching the opposite boundary. By comparison, a beam of light requires only 8 minutes and 20 seconds to travel from the Sun to Earth, and roughly 5.5 hours to cross the average distance between the Sun and Pluto. The fact that light requires more than 4 days to traverse the dark shadow of TON 618 underscores the vast physical volume enclosed within its gravitational reach. Calculating the volume enclosed within this 390 billion kilometer boundary illustrates another fascinating relativistic property of ultramassive black holes. Volume scales with the cube of the radius according to standard spherical geometry. Substituting the 195 billion kilometer radius into the volume equation for a sphere yields a spatial volume measuring approximately 31 septillion cubic kilometers. This immense volume of enclosed space creates a surprising physical phenomenon regarding average mass density. In classical astrophysics, black holes are frequently conceptualized as objects of extreme, near-infinite mass density. For stellar mass black holes, this description is entirely accurate. A black hole of 3 solar masses compresses its material into such a small spatial volume that the average density within its event horizon vastly exceeds the nuclear density of an atomic nucleus, reaching values above trillions of kilograms per cubic meter. However, because the mass of a black hole increases linearly, while its volume increases with the cube of its radius, the overall average density within the event horizon decreases dramatically as the total mass grows. The average density of a black hole is calculated by dividing its total mass by the volume enclosed within its Schwarzschild radius. When this density calculation is performed for TON 618, dividing 66 billion solar masses by its 31 septillion cubic kilometer volume, the resulting average mass density inside its event horizon is remarkably low. The average density of TON 618 works out to approximately 12 grams per cubic meter. To put this value into an everyday context, 12 grams per cubic meter is significantly less dense than the air we breathe at sea level on Earth, which has a density of approximately 1,200 grams per cubic meter. In fact, the average density within the event horizon of TON 618 is roughly 100 times less dense than terrestrial air. If a human could theoretically survive the high-energy radiation environment and stand within a sealed habitat containing a cubic meter of the space enclosed inside TON 618's event horizon, prior to reaching the central singularity, the total mass contained within that cubic volume of space would weigh less than an empty aluminium soda can. This counterintuitive physical reality highlights that an ultramassive black hole does not achieve its extreme gravitational power through ultra-dense material packed evenly across its volume. Rather, it achieves its immense scale through the pure, overwhelming sum of its total mass curving a colossal volume of surrounding space. However, despite this low average spatial density, the tidal forces and gravitational acceleration near the core remain absolute. The mathematical concept of the Schwarzschild radius provides astrophysicists with a precise frame of reference for mapping the extreme geometry of space around TON 618. A dark sphere spanning 390 billion kilometers across, surrounded by a swirling, incandescent accretion disk glowing with the power of 140 trillion suns, represents one of the most mathematically profound and physically daunting structures permitted by the laws of modern physics. To fully grasp the gargantuan physical scale of TON 618, theoretical comparisons using raw numbers in billions of kilometers are often insufficient for human imagination. A powerful method for comprehending this behemoth is a thought experiment, placing the central engine of TON 618 at the absolute center of our solar system, replacing our Sun. In this hypothetical scenario, the immediate consequences illustrate not only the vastness of the black hole's event horizon, but also how thoroughly it would swallow our entire cosmic neighborhood. If TON 618 were positioned where our Sun sits today, its event horizon, the pitch-black sphere marking the point of no return, would instantly erase the inner solar system. Mercury, orbiting at an average distance of 57.9 million kilometers, would be completely submerged inside the dark singularity, deep within its interior volume. Venus, situated at 108 million kilometers, and Earth, located at 149.6 million kilometers, would vanish without a trace. Mars, orbiting at 228 million kilometers, would similarly cease to exist, engulfed thousands of times over within the vast abyss of the event horizon. Moving outward into the realm of the gas giants, the scale of Ton 618 becomes even more terrifying. Jupiter orbits the Sun at an average distance of roughly 778 million kilometers. Saturn lies at a distance of 1.4 billion kilometers. Uranus orbits at 2.8 billion kilometers, and Neptune, the outermost recognized major planet in our solar system, circles at 4.5 billion kilometers. If Ton 618 sat at the solar position, all four gas giants, along with their complex systems of moons, rings, and surrounding space, would be swept up and lost inside the dark central sphere. Even dwarf planets positioned far beyond the main planetary domain would fail to escape the event horizon's reach. Pluto, which follows an eccentric elliptical orbit carrying it between 4.4 billion and 7.3 billion kilometers from the Sun, would lie completely inside the threshold. The Kuiper Belt, a vast torus of icy bodies extending from roughly 30 astronomical units to 50 astronomical units, or roughly 7.5 billion kilometers, would be entirely consumed. Eris, Sedna, and Makemake, distant icy worlds lurking in the frozen fringes of our system, would all sink beneath the 390 billion kilometer diameter threshold of Ton 618. In fact, one must travel far past the traditional boundaries of the solar system to reach the physical edge of Ton 618's event horizon. The boundary of the black hole would extend outward to approximately 130 astronomical units in radius, a distance of 195 billion kilometers from the center. To put this into perspective, Voyager 1, humanity's most distant robotic probe launched in 1977, has been traveling outward at speeds exceeding 38,000 miles per hour for nearly half a century. As of the current era, Voyager 1 is located roughly 160 astronomical units away from Earth, having barely managed to cross beyond the heliosphere into interstellar space. If Ton 618 were placed at the center of our solar system, Voyager 1 would only just now be approaching the outer edge of its event horizon after decades of non-stop travel. Beyond the Kuiper Belt lies the theoretical realm of the inner Oort cloud, a vast reservoir of icy planetesimals surrounding the Sun. The inner edge of the Oort cloud is estimated to begin between 200 and 2,000 astronomical units away. This means that the physical event horizon of Ton 618 alone would swallow the entire planetary solar system, the Kuiper Belt, and reach into the innermost boundary of the Oort cloud itself. Furthermore, this scale accounts only for the black hole's shadow, the event horizon. If one includes the brilliant, swirling accretion disk surrounding Ton 618, which extends for thousands of astronomical units beyond the event horizon, the entire outer Oort cloud would be enveloped in superheated plasma glowing at hundreds of thousands of degrees. Comparing Ton 618 to the solar system brings us back to a profound scientific question. How can an object that swallows entire solar systems whole have an average mass density less than that of Earth's atmosphere? This phenomenon is often called the black hole density paradox, and it reveals a deep fundamental truth about how general relativity governs spatial volume. In human experience, density is an intuitive property. We expect larger, heavier objects made of matter to become increasingly dense as mass is packed tightly together. A lead brick is denser than a wooden block, and a neutron star, where a stellar mass is crushed into a sphere 20 kilometers across, boasts an extreme density of hundreds of trillions of grams per cubic centimeter. However, black holes operate under unique mathematical scaling laws because the event horizon is a mathematical coordinate boundary of curved space-time, not a solid material surface. As established by the Schwarzschild radius formula, the radius of a black hole increases linearly with its mass. If you double the mass, you double the radius. However, basic Euclidean geometry dictates that the volume of a sphere scales with the cube of its radius. This difference between linear mass growth and cubic volume growth produces a surprising mathematical relationship for density. When mass increases by a factor of 10, the radius also increases by a factor of 10, but the spatial volume enclosed within the event horizon increases by a factor of 1,000. Because density equals mass divided by volume, multiplying mass by 10 while multiplying volume by 1,000 results in an overall density that is 100 times smaller than before. As a black hole grows larger and more massive, the spatial volume inside its event horizon expands at a dramatically faster rate than the mass itself. For small stellar mass black holes, such as a black hole possessing 10 times the mass of our Sun, the Schwarzschild radius is only 30 kilometers, enclosing a tiny volume. Dividing 10 solar masses by that small volume yields an average mass density of roughly 100 quadrillion grams per cubic centimeter, denser than an atomic nucleus. If a supermassive black hole reaches 4 million solar masses, like Sagittarius A star at the center of our galaxy, its density drops to roughly the density of water. By the time a black hole reaches the ultramassive scale of Ton 618, with 66 billion solar masses, the volume enclosed within its 195 billion kilometer radius becomes enormous, exceeding 31 septillion cubic kilometers. Dividing 66 billion solar masses by this vast spatial volume yields an average mass density of approximately 12 grams per cubic meter. As noted previously, this value is roughly 100 times less dense than the ambient air found at sea level on Earth. This low average density creates a fascinating conceptual scenario for a theoretical astronaut approaching Ton 618. For smaller stellar mass black holes, the gravitational gradient near the event horizon is steep. The difference in gravitational pull between an astronaut's feet and head, known as tidal force, is so violent that an observer is stretched and torn apart through spaghettification long before ever reaching the threshold. However, for an ultramassive black hole like Ton 618, the vast physical radius of 195 billion kilometers spreads the gravitational gradient across an immense spatial volume. Consequently, the tidal forces at the event horizon of Ton 618 are gentle. An astronaut crossing the 390 billion kilometer threshold would feel virtually no disruptive tidal pull at the moment of entry. They could cross the point of no return without experiencing any physical discomfort, completely unaware of the threshold except for the dramatic optical warping of space around them. Only as they fell much deeper toward the central singularity, hours or days later, would the gravitational tidal forces finally become destructive. This density scaling law leads astrophysicists to a fascinating conclusion. The largest structures in the universe are, in terms of average spatial enclosure, surprisingly diffuse. Ton 618 dominates its realm not by packing dense material tightly throughout a volume, but by commanding a region of spacetime so vast that its gravitational influence shapes entire galaxies. Placing Ton 618 within the frame of our solar system highlights the gap between human scales and cosmological realities, confirming its status as one of the most terrifyingly massive entities in the known universe. To fully appreciate the extraordinary place Ton 618 occupies within the architecture of the cosmos, one must examine the broader taxonomy used by modern astrophysicists to classify black holes. Black holes are not uniform entities. They span a spectrum of masses, physical dimensions, and evolutionary pathways. Historically, scientists categorized these gravitational abysses into simple tiers based on how they formed and how much mass they accumulated. However, as observational technology advanced and revealed titans that surpassed standard theoretical expectations, this classification scheme had to expand. Ton 618 sits at the absolute summit of this hierarchy, serving as the benchmark for the most extreme physical boundaries permitted by the laws of nature. At the lowest end of the mass spectrum lie microblack holes, also known as quantum mechanical or primordial black holes. These entities are entirely hypothetical within contemporary physics, as none have been observed directly. Theoretical models suggest that microblack holes could have formed during the hyperdense, turbulent conditions of the cosmic inflation era immediately following the Big Bang. Their masses could range from a fraction of a gram up to the mass of a planet or moon, yet their physical Schwarzschild radii would measure less than the diameter of a single subatomic particle. Due to quantum effects described by theoretical physicist Stephen Hawking, microblack holes are predicted to lose mass through quantum evaporation over time, with the smallest among them evaporating almost instantly in violent flashes of high-energy gamma radiation. The first empirically confirmed class of black holes consists of stellar mass black holes. These objects are the natural endpoint of massive star evolution. When a star with an initial mass greater than roughly 20 solar masses consumes its internal nuclear fuel, it can no longer generate the outward thermal radiation pressure required to balance its own immense gravity. The core collapses catastrophically during a supernova event, compressing several solar masses of material into a singularity. Stellar mass black holes typically range from roughly 3 solar masses, the theoretical lower bound set by the Tolman-Oppenheimer-Volkoff limit for neutron star stability, up to approximately 100 solar masses. Their event horizons span physical diameters ranging from a few kilometers to several hundred kilometers, making them tiny on a cosmic scale, though exceptionally dense. Positioned between stellar mass black holes and their truly colossal cousins are intermediate mass black holes. Possessing masses ranging from roughly 100 solar masses to 100,000 solar masses, these targets represent a critical missing link in observational astronomy. For decades, intermediate mass black holes proved elusive, but recent gravitational wave detections by observatories such as LIGO and Virgo, alongside high-resolution space telescope observations of globular clusters, have confirmed their existence. Intermediate mass black holes are believed to form through runaway mergers of stellar mass black holes in dense star clusters, or through the direct collapse of massive primordial gas clouds in the early universe. Beyond the intermediate realm lies the category of supermassive black holes. Defined as black holes possessing masses ranging from hundreds of thousands to tens of billions of solar masses, these monsters reside at the dynamic centers of virtually every mature galaxy in the universe. Our own galaxy, the Milky Way, harbors Sagittarius A star, a supermassive black hole containing roughly 4 million solar masses. While 4 million solar masses is immense compared to stellar standards, Sagittarius A star is relatively modest when evaluated against the supermassive black holes found in major elliptical galaxies. For instance, Messier 87 contains a supermassive black hole weighing approximately 6.5 billion solar masses, spanning an event horizon wider than our entire planetary solar system. However, when astrophysicists analyzed objects like TUN 618, they realized that the standard supermassive designation was insufficient to capture their true physical scale. This led to the creation of a higher classification tier, ultramassive black holes, reserved exclusively for black holes with masses exceeding 10 billion solar masses. This class represents the true leviathans of the cosmos. TUN 618, with its estimated mass of 66 billion solar masses, stands as one of the ultimate members of this elite group. The discovery of ultramassive black holes immediately forced theoretical physicists to grapple with a fundamental question. Is there an absolute upper limit to how large a black hole can grow through traditional accretion? In the realm of physical laws, infinite growth is rarely permitted. For black holes powering active galactic nuclei, 2 primary mechanisms govern the theoretical maximum mass limit: radiation pressure dynamics and accretion disk stability. The primary physical barrier to continuous black hole growth is established by the interaction between gravity and radiation pressure, formalized by the Eddington limit. As matter falls toward a black hole, it heats up within the accretion disk and streams high-energy photons outward into space. If the accretion rate becomes too intense, the outward radiation pressure exceeds the inward gravitational pull, blowing away surrounding gas and starving the central engine. While a black hole can briefly undergo super-Eddington accretion, swallowing material faster than radiation pressure can push it away, this phase is typically self-limiting on cosmic timescales, as surrounding gas reservoirs are cleared out or blown away into intergalactic space. Beyond the Eddington limit, an even more fundamental physical barrier involves the thermodynamic stability of the accretion disk itself. Research conducted by astrophysicists studying active galactic nuclei demonstrates that as a central black hole grows more massive, the physical point where the accretion disk must form pushes further outward into regions where gas densities and temperatures drop. For a black hole approaching tens of billions of solar masses, the outer regions of the accretion disk become so massive and cool that the gas undergoes gravitational fragmentation. Instead of remaining a smooth, viscous plasma disk feeding material smoothly inward toward the event horizon, the outer disk fragments into dense clouds that rapidly collapse under their own local gravity to form stars. Once gas forms stars, those stars orbit the central mass peacefully in stable trajectories, rather than spiraling inward to feed the black hole. Consequently, the accretion disk effectively destabilizes and vanishes, shutting off the supply of infalling fuel. Theoretical models calculating this disk fragmentation limit suggest that for standard black holes feeding via stable, thin accretion disks, the maximum mass threshold is approximately 50 to 60 billion solar masses. This theoretical boundary makes the 66 billion solar mass value of TON 618 particularly intriguing. TON 618 sits directly at, or slightly above, the traditional theoretical maximum mass limit predicted for active accretion disks. This proximity to the theoretical ceiling implies that TON 618 may have reached the absolute summit of what standard accretion physics can achieve in our universe, or that it accumulated its mass through unique high-density growth phases during the early cosmological era. To account for theoretical entities that might surpass standard accretion boundaries, astrophysicists have proposed an even more extreme conceptual category: stupendously large black holes, frequently referred to by the acronym SLABs. While ultramassive black holes like TON 618 are capped near 50 to 100 billion solar masses by accretion disk dynamics, the hypothetical SLAB framework considers black holes possessing masses ranging from 100 billion to over 100 trillion solar masses. Because no known active accretion process could build a black hole to 100 trillion solar masses within the current age of the universe, SLABs cannot form through standard stellar evolution or galactic accretion. Instead, if stupendously large black holes exist, they must have originated through non-standard cosmological mechanisms in the earliest moments following the Big Bang. Proposed mechanisms include the direct, non-linear collapse of primordial density fluctuations during the radiation-dominated era, or violent runaway mergers of primordial seeds before the formation of the first stars. If a stupendously large black hole with a mass of 100 trillion solar masses were to exist somewhere in the cosmic web, its physical dimensions would stagger the imagination. Its Schwarzschild radius would extend for nearly 1 light-year into space, spanning a physical diameter of 2 light-years across. Its event horizon alone would encompass space large enough to hold multiple nearby star systems. However, because such an object would possess an extremely low average density and lack a stable luminous accretion disk, detecting a non-accreting slab at vast cosmological distances remains an extraordinary observational challenge. Within this hierarchical spectrum, ranging from invisible micro-black holes up to theoretical trillion solar mass slabs, TON 618 occupies a crucial real-world position. It is not an abstract mathematical exercise or a theoretical construct. It is a physical entity that has been directly detected and analysed across multiple regions of the electromagnetic spectrum. It represents the observational maximum of physical reality, sitting squarely at the pinnacle of the ultramassive black hole classification. By categorising objects like TON 618, astrophysicists gain vital insight into the evolutionary boundaries of our universe. The taxonomy of black holes is not merely about assigning arbitrary labels based on size. It reflects the underlying physics governing cosmic structures at different epochs of time. From stellar remnants that dot our local galactic neighbourhood to the ultramassive Leviathan powering TON 618 at a redshift of 2.219, these gravitational anchors illustrate how gravity organises mass across every scale permitted by the laws of nature. The existence of TON 618 presents one of the most significant theoretical crises in modern observational cosmology. When astrophysicists analyse the light reaching Earth from this hyperluminous quasar, they are observing an entity that existed 10.4 billion years ago, when the universe was only about 3.4 billion years old. Containing an estimated 66 billion solar masses at such an early epoch, TON 618 forces scientists to confront a fundamental paradox. According to standard models of stellar evolution and cosmic growth, there simply was not enough time between the Big Bang and 3.4 billion years of cosmic time for a central singularity to assemble that much mass. To understand why TON 618 poses such a profound challenge, one must examine the standard theoretical framework for black hole growth. In conventional astrophysical models, black holes begin as stellar mass remnants created by the catastrophic core collapse of massive stars. These initial seed black holes typically possess masses ranging from 10 to 100 times that of our Sun. To grow into a supermassive or ultramassive black hole, a seed must continuously draw in surrounding gas, dust, and stars through gravitational accretion, or merge with other black holes during galactic collisions. However, the rate at which a black hole can continuously devour matter is strictly governed by physical laws. As infalling gas spirals into an accretion disk, it converts gravitational potential energy into thermal radiation. The resulting radiation pressure pushes outward against the incoming matter. The theoretical ceiling for this balance is defined by the Eddington limit, which dictates the maximum luminosity and corresponding accretion rate a black hole can sustain without blowing away its fuel supply. Under steady Eddington-limited accretion, a black hole's mass increases exponentially over time. The characteristic timescale required for a black hole to double its mass while accreting at the Eddington limit, assuming a standard mass-energy conversion efficiency of roughly 10%, is known as the E-folding time, or the Salpeter timescale, which equals approximately 45 million years. If a stellar mass seed of 10 solar masses begins growing shortly after the formation of the first stars, continuous accretion at the Eddington limit without interruption would require over 1 billion years just to reach a few million solar masses, and significantly longer than the age of the universe at redshift 2.219 to reach 66 billion solar masses. Furthermore, real cosmic environments rarely allow for continuous, uninterrupted Eddington accretion over billions of years. Supernova feedback, radiation-driven galactic winds, and magnetic turbulence frequently disrupt gas inflows, starving the central black hole and shutting down accretion for extended periods. Given these realistic environmental constraints, growing a seed black hole from tens of solar masses to tens of billions of solar masses within 3.4 billion years is mathematically improbable under standard models. This stark contradiction between observed physical scale and available growth time is known as the early supermassive black hole paradox. To resolve this paradox, theoretical astrophysicists have proposed several competing hypotheses regarding the origins and growth mechanisms of high redshift giants like TON 618. Because direct observational evidence from the early universe remains limited, these theoretical models are actively debated within the scientific community, with each framework presenting unique advantages and physical challenges. The first major theoretical avenue involves the heavy seed hypothesis, specifically through the process known as direct collapse. Rather than starting from a small stellar mass seed of 10 to 100 solar masses, direct collapse models propose that much larger seed black holes, possessing masses between 10,000 and 1 million solar masses, formed directly in the early universe without passing through a traditional stellar phase. In the pristine conditions of the early cosmos, massive pristine clouds composed entirely of primordial hydrogen and helium gas collected within dark matter halos. If these gas clouds lacked heavy chemical elements, metals forged in earlier star generations, they could not efficiently cool through atomic and molecular line emission. Without efficient cooling, the gas cloud resisted fragmenting into thousands of smaller ordinary stars. Under specific environmental conditions, such as being illuminated by intense background ultraviolet radiation from nearby star-forming regions that destroyed molecular hydrogen, the immense gas cloud could collapse directly under its own gravitational weight. This direct gravitational collapse would yield a short-lived intermediate state known as a quasi-star or a supermassive star, where a dense central core collapses into a black hole while enveloped in a massive expanding envelope of gas. The central seed black hole rapidly devours the surrounding envelope from the inside out, yielding a massive seed black hole of 100,000 to 1 million solar masses within a few million years. By starting the evolutionary journey with a seed that is already 1 million times more massive than a standard stellar remnant, the total time required for subsequent accretion to reach 66 billion solar masses is drastically reduced, allowing TON 618 to fit within the 3.4 billion-year cosmic window. While the direct collapse hypothesis elegantly bypasses the time constraint by providing massive initial seeds, it relies on strict environmental conditions. Pristine, metal-free gas clouds bathed in precise ultraviolet radiation fields while avoiding star formation may have been rare in the early universe, prompting astrophysicists to explore alternative growth mechanisms. A second leading hypothesis focuses on periods of super-Eddington accretion. The standard Eddington limit assumes a spherical geometry and steady-state thermodynamic equilibrium where radiation streams freely through infalling gas. However, realistic accretion disks are complex three-dimensional environments governed by fluid dynamics, magnetic fields, and anisotropic radiation fields. Under certain conditions, such as hyperdense gas inflows triggered by violent major galaxy mergers in the early universe, infalling gas can pile up around the central engine at rates vastly exceeding the theoretical Eddington threshold. In these slim accretion disks, or photon-trapping disks, the inward flow of matter is so rapid and dense that generated radiation becomes trapped within the gas flow, rather than escaping outward. Instead of radiation pressure blowing the fuel away, photons are dragged inward across the event horizon alongside the infalling mass. If a black hole undergoes extended episodes of super-Eddington accretion, its mass growth rate transitions from a slow exponential curve to rapid hypergrowth, doubling its mass on timescales much shorter than the standard 45 million-year Salpeter timescale. Through repeated or sustained super-Eddington accretion phases, even a modest stellar mass seed or intermediate mass seed could rapidly expand into an ultramassive black hole within a few hundred million years, providing a plausible mechanism for assembling 66 billion solar masses by redshift 2.219. A third theoretical perspective suggests that primordial black holes, originating in the immediate aftermath of the Big Bang, provided the initial foundational masses for hyperluminous quasars. Unlike astrophysical black holes created by stellar collapse, primordial black holes are hypothesized to have formed during the first fraction of a second after the Big Bang, when extreme density fluctuations in the expanding space-time collapsed directly into singularities. Depending on the scale of these density fluctuations, primordial black holes could have been born across a wide mass spectrum, ranging from microscale objects to massive seeds weighing thousands or millions of solar masses long before the first stars ever ignited. If massive primordial black holes seeded the cosmic web during the inflationary epoch, they would have acted as immediate gravitational anchors in the early universe, attracting pristine gas and dark matter from their inception. Under this scenario, TON 618 did not need to build its mass entirely through stellar evolution. It inherited a substantial head start from the high-density physics of the infant cosmos. A fourth complementary hypothesis emphasizes violent major mergers within dense protoclusters in the early universe. The early universe was significantly smaller and denser than it is today, with developing galaxies positioned much closer together. Protoclusters contained high concentrations of gas-rich galaxies undergoing frequent, violent collisions. When two young galaxies merge, their central black holes eventually sink toward the center of the newly formed galaxy through dynamical friction, forming a bound binary black hole system. Over time, gravitational wave emission and interactions with surrounding stars cause the binary orbit to decay, leading to a catastrophic merger that combines the masses of both central engines. If a growing central black hole undergoes multiple sequential major mergers with other supermassive and intermediate black holes within a hyperdense cosmic node, its mass can increase in large discrete jumps rather than relying solely on steady gas accretion. Combining major black hole mergers with high-density accretion episodes presents a multi-channel growth pathway capable of constructing ultramassive leviathans. Each of these theoretical models, direct collapse heavy seeds, super-Eddington accretion, primordial black hole seeds and runaway merger networks, offers a distinct physical mechanism to explain the early existence of TON 618. Modern astrophysics does not treat these hypotheses as mutually exclusive. Rather, the reality may involve a complex combination of these processes operating in tandem within the unique environments of the early universe. Observational testing of these competing frameworks has advanced dramatically with the deployment of next-generation astronomical observatories, such as the James Webb Space Telescope, and advanced radio interferometers like the Atacama Large Millimeter Submillimeter Array. By capturing infrared light from high-redshift quasars and galaxies at redshifts exceeding 6, 7, and 8, astronomers are discovering an unexpectedly dense population of massive black holes existing within the first billion years of cosmic history. These ongoing observational discoveries continue to refine mathematical models of early cosmic structure formation. TUN 618 stands as a monument to this unresolved scientific mystery. By pushing standard growth models to their absolute mathematical limits, this 66 billion solar mass titan serves as an indispensable laboratory, forcing theoretical physicists to continuously re-evaluate how matter, radiation, and gravity interacted during the formative epoch of our universe. Behind the blinding glare of the central engine of TUN 618 lies an entire galactic environment completely overshadowed by the light of its core. In standard galaxy evolution models, a supermassive black hole resides at the dynamical center of a surrounding stellar metropolis containing millions or billions of stars, vast gas reservoirs, and complex dark matter halos. However, observing the host galaxy of a hyperluminous quasar like TUN 618 presents an extraordinary observational challenge. The total optical and ultraviolet luminosity of TUN 618 outshines its surrounding host galaxy by a factor of hundreds or even thousands. The host galaxy is virtually drowned in an ocean of radiation, making its direct optical visualization almost impossible with standard imaging techniques. Despite this blinding glare, astrophysicists use high-resolution submillimeter interferometry, space-based infrared imaging, and numerical simulations to reconstruct the likely properties of the galaxy housing this giant. A black hole of 66 billion solar masses cannot exist in isolation. It requires an equally massive cosmic structure to supply the raw gas and gravitational binding energy needed to grow and sustain such an engine. The host galaxy of TUN 618 is hypothesized to be a monster in its own right, a hyperluminous giant elliptical galaxy or a protocluster brightest cluster galaxy, situated at the nexus of a vast cosmic web filament in the early universe. In the local universe, a well-established empirical relationship exists between the mass of a central supermassive black hole and the total mass of its host galaxy's stellar bulge, known as the M-sigma relation. Under standard local scaling laws, a central black hole typically accounts for roughly 0.1% of the total stellar mass of its host galaxy's bulge. If this standard local scaling relation held true for TUN 618 at a redshift of 2.219, a 66 billion solar mass black hole would imply a host galaxy possessing a stellar mass measuring in tens of trillions of solar masses, a structure vastly more massive than any galaxy known to exist in the observable universe. This glaring discrepancy indicates that the evolutionary relationship between central black holes and their host galaxies was fundamentally different during the early cosmological era. In the young universe, central black holes appear to have grown far more rapidly than their surrounding stellar populations, overgrowing their host galaxies and breaking local scaling relations. The host galaxy of TUN 618 was likely an extremely dense, highly gas-rich system where central black hole growth dramatically outpaced the rate of galactic star formation. The environment within this host galaxy is defined by violent, energetic interactions known as active galactic nucleus feedback. An active central black hole does not merely absorb matter from its environment, it violently interacts with the entire galactic ecosystem through the release of continuous, colossal energy flows. In hyperluminous radio-loud quasars like TUN 618, this feedback operates through two primary modes: radiative mode, also known as wind mode, and kinetic mode, also driven by relativistic jets. In the radiative mode, the intense radiation pressure generated by the accretion disk transfers momentum directly to surrounding gas clouds within the host galaxy. As light streams outward from the inner light years, it strikes dust grains and ionized plasma throughout the interstellar medium. This continuous photon pressure drives high-velocity galactic winds that sweep through the galaxy at speeds reaching several thousand kilometers per second. These radiative winds displace gas, heating pristine star-forming clouds and pushing vast reservoirs of hydrogen out of the galactic core. Simultaneously, kinetic feedback operates through the launch of powerful relativistic jets. As superheated plasma approaches the event horizon of TON 618, intense magnetic fields anchored in the rotating accretion disk and space-time frame dragging funnel a portion of the infalling matter away from the central engine. This matter is accelerated to significant fractions of the speed of light and launched outward in two oppositely directed, highly collimated streams perpendicular to the accretion disk. These relativistic jets extend far beyond the physical boundaries of the central accretion disk, carving their way through the host galaxy's interstellar medium and penetrating deep into the surrounding intergalactic medium. As the high-energy particles within the jets plow into ambient galactic gas, they create shockwaves that heat cold interstellar gas from a few dozen Kelvin up to millions of degrees. This intense heating and displacement of interstellar gas triggers a profound astrophysical transformation within the host galaxy, known as quasar quenching. To form new stars, a galaxy requires vast reservoirs of cold, dense molecular gas, primarily molecular hydrogen. Under cool, low-energy conditions, gravity overcomes internal gas pressure, causing dense cloud cores to collapse into young stars. However, when the central engine of TON 618 floods the galaxy with high-energy radiative winds and jet-driven shockwaves, the cold molecular gas is subjected to violent thermal energy injection. The gas becomes completely ionized, superheated, and turbulent. Hyperthermal gas possesses immense kinetic pressure that completely counteracts gravitational collapse, preventing the gas from cooling and fragmenting into star-forming cores. Furthermore, the sheer physical force of the radiative winds and relativistic jets can eject millions of solar masses of cold gas completely out of the host galaxy into intergalactic space every single year. This dual process, heating cold gas reservoirs and physically expelling fuel out of the gravitational potential well, effectively halts all star formation throughout the host galaxy. A galaxy that may have once experienced intense starburst activity is abruptly strangled by its own central black hole. The host galaxy transitions from an active, star-forming system into a quiescent, dying galaxy composed primarily of aging, low-mass stars. TON 618 acts as an absolute master of its host galaxy, controlling its stellar population and determining its ultimate fate. Extending outward from the host galaxy itself is the large-scale cosmic environment surrounding TON 618. In cosmological structure models, hyperluminous quasars do not form in empty regions of space. They assemble at the highest density peaks of the primordial dark matter distribution, sitting at the intersection nodes of the cosmic web. Surrounding the host galaxy of TON 618 is a high-density protocluster containing dozens or even hundreds of smaller satellite galaxies embedded in a vast halo of dark matter. The gravitational pull of the 66 billion solar mass central engine, combined with the massive dark matter halo, continuously draws nearby satellite galaxies inward toward the center. Over cosmic time, these satellite galaxies undergo dynamical friction, spiraling inward and merging with the primary host galaxy. This continuous process of galactic cannibalism feeds both the central black hole and the outer stellar halo of the host system, contributing to the assembly of a giant elliptical galaxy. However, while galactic cannibalism brings new gas into the host galaxy, the continuous energetic feedback from TON 618 regulates how much of that gas can actually settle onto the central engine or form new stars. The relativistic jets act as a thermostat for the entire protocluster environment. As cold gas streams inward from the cosmic web filaments toward the central galaxy, it encounters the high-energy bubbles blown by the jets in the intracluster medium. The jets heat the infalling intracluster gas, preventing runaway cooling flows and maintaining a delicate thermal equilibrium across millions of light-years of surrounding space. Observing these jet-driven structures in high-redshift quasars provides astrophysicists with crucial insights into how energy is transferred across astronomical scales. The central engine of TON 618, with an event horizon measuring 390 billion kilometers across, directly influences gas dynamics across a host galaxy, spanning tens or hundreds of thousands of light years, and shapes the intergalactic medium across megaparsecs of space. The scale of this influence represents a spatial dynamic spanning more than 12 orders of magnitude. Analyzing the spectrum of TON 618 provides direct observational evidence of these massive outflows. High-resolution optical and ultraviolet spectroscopy reveals broad absorption line features shifted towards shorter wavelengths relative to the systemic redshift of the quasar. These blue shifted absorption lines trace gas clouds moving rapidly toward the observer, physically documenting high-velocity galactic winds driven away from the central core at speeds reaching substantial percentages of the speed of light. Furthermore, radio observations using ground-based radio telescope arrays map extended synchrotron emission originating from the relativistic jet lobes surrounding TON 618. These radio lobes display intense non-thermal emission generated by high-energy electrons spiraling around strong magnetic fields. The vast spatial extension of these radio lobes confirms that kinetic energy launched from the central engine has been actively interacting with surrounding gas for millions of years. The host galaxy of TON 618 represents its extreme environment governed by feedback physics. It is a world where the central black hole dominates every physical process, dictating the thermal state of the interstellar medium, turning off star formation, driving vast galactic winds, and shaping the evolution of an entire surrounding cosmic node. Beneath the blinding glare of the most luminous engine in the early universe sits a host galaxy, transformed by the gravitational and radiative titan at its heart. Understanding the true present-day status of TON 618 requires embracing the vast cosmic timescales imposed by the finite speed of light. Because TON 618 is located 10.4 billion light-years away from Earth, the light collected by our modern telescopes today was emitted 10.4 billion years ago. We are observing TON 618 as it existed in its youthful hyperluminous quasar phase, when the universe was only 3.4 billion years old. What we see on our sky is not a live broadcast of the present moment, but an ancient snapshot preserved across billions of light-years of expanding space. In the contemporary cosmic present, 10.4 billion years after emitting the light we see today, TON 618 has evolved into a vastly different entity. Over the intervening billions of years, the hyperactive accretion engine that once powered 140 trillion solar luminosities inevitably depleted its surrounding gas reservoirs. Through violent radiative feedback, relativistic jet quenching, and steady consumption, the central black hole cleared out the dense gas clouds in its immediate vicinity. Lacking a continuous inflow of pristine cold hydrogen to sustain hyper-efficient accretion, the brilliant quasar engine powered down, leaving behind a dormant, dark, ultramassive black hole. Today, sitting quietly at the core of a massive, evolved elliptical galaxy, the central singularity of TON 618 remains as massive as ever, potentially having accumulated even more mass through subsequent galaxy mergers. It no longer shines with blinding intensity across the electromagnetic spectrum. Instead, it exists as a dark gravitational anchor in the modern cosmos. It wanders silently through space, invisible to optical instruments except through the gravitational lensing of background light or occasional tidal disruption events when a stray star passes too close to its event horizon and is torn apart by tidal forces. Looking forward into the far future of the cosmos, theoretical physics provides a framework for predicting the ultimate fate of TON 618 across timescales that surpass human comprehension. As the universe continues its accelerating expansion driven by dark energy, stars will exhaust their nuclear fuel and collapse into cold remnants. Over trillions of years, galaxies will cease forming new stars, entering the degenerate era, and eventually transitioning into the black hole era. In this distant cosmic epoch, roughly 100 trillion years from now, ordinary matter will have decayed or collapsed, leaving black holes as the dominant macrostructures inhabiting an expanding, darkened universe. Even in this dark future, black holes are not completely immortal. According to theoretical work published by Stephen Hawking in 1974, quantum mechanical effects near the event horizon cause black holes to slowly emit thermal radiation, a process known as Hawking radiation. In quantum field theory, particle-antiparticle pairs constantly fluctuate into existence near the event horizon. Occasionally, one particle falls into the singularity, while the other escapes into space as thermal radiation. The energy carried away by the escaping particle reduces the total mass of the black hole, according to the mass-energy equivalence principle. However, the temperature of Hawking radiation is inversely proportional to the mass of the black hole. A black hole as colossal as Ton 618 possesses an extraordinarily low Hawking temperature, measuring near absolute zero, far colder than the current temperature of the cosmic microwave background radiation. Consequently, as long as the cosmic microwave background remains warmer than the Hawking temperature of Ton 618, the black hole actually absorbs more energy from background radiation than it emits through quantum evaporation, causing it to continue growing slightly, even in deep space. Only when the universe expands and cools far below the Hawking temperature of ultramassive black holes will Ton 618 begin the agonizingly slow process of net mass loss through Hawking radiation. Because mass evaporation scales cubically with total mass, the lifespan of an ultramassive black hole is absurdly long. While a stellar mass black hole might evaporate in 10 to the power of 67 years, a 66 billion solar mass leviathan like Ton 618 requires a timescale on the order of 10 to the power of 100 years to completely radiate its mass away. During this vast epoch, Ton 618 will slowly lose mass over uncounted eons, steadily shrinking in radius, while its Hawking temperature imperceptibly increases. In its final moments, once its mass is reduced to a microscopic scale, the remaining mass will evaporate in a high-energy flash of gamma rays and elementary particles, finally dissolving the central anchor back into the expanding quantum void of an empty universe. Beyond its extreme physical parameters and ultimate future fate, Ton 618 holds profound significance for contemporary physics and observational cosmology. It serves as an extreme natural laboratory that tests the absolute boundaries of our theoretical frameworks. In theoretical physics, Albert Einstein's general theory of relativity has successfully passed every test conducted within our local solar system and galaxy. However, testing general relativity under the extreme gravitational conditions created by 66 billion solar masses allows theoretical physicists to verify whether space-time curvature behaves as predicted near maximum physical thresholds. Furthermore, Ton 618 remains a central challenge for models of early universe structure formation and high-energy particle dynamics. Its existence forces cosmologists to continually refine theories regarding dark matter halo assembly, primordial gas collapse, and nonlinear accretion processes in the infant universe. By acting as an empirical benchmark for maximum black hole growth, Ton 618 provides the necessary boundary conditions that prevent cosmological simulations from using unrealistic physics. In summary, Ton 618 is far more than a simple cosmic curiosity or a statistical outlier in an astronomical database. From its humble beginning as a misidentified dim blue dot on a photographic plate in Mexico to its current status as one of the most massive entities ever catalogued, Ton 618 challenges human intuition regarding scale, distance, time. It represents the supreme triumph of human curiosity, our ability to use physics, mathematics, and optical spectroscopy to reach across 10.4 billion light-years of space, map a dark sphere spanning 390 billion kilometers across, and measure an object that outshone entire galaxies at the dawn of time.